So recall we talked about the fundamental theorem of Galois theory. So what we'll do is say a few more things about it. So continued. So observe that the following is really the main content of the theorem, that if I have a Galois extension K over F, so here's a finite Galois extension K over F, then the intermediate subfields of this extension are in bijection with the, let's draw the group picture on the other side. This is the automorphisms of K over F. This is the identity subgroup, and I can look at subgroups of G. So subgroups by definition are necessarily subsets of G which contain the identity. So these intermediate extensions E are in bijection with the subgroups of G. Okay, and this map is sometimes called the Galois correspondence. So there are sort of maps in both directions. We know how to given H, E is obtained as the fixed field of H, and given E, H is obtained as the automorphisms of K which are identity on E. Okay. Now the one thing that we did say as part of the proof of this bijective correspondence is that if K over F is Galois, then so is K over E. Okay, so this is also automatically a Galois extension, and so in fact let's just write this down. K over F is a Galois extension, implies, in fact this is true even if it's not finite. K over E is Galois, and that just followed because of we use the normal and separable definition. You just have to check that when you think of K as an extension of E, it continues to be normal and separable. Okay. However, the same is not true of E thought of as an extension over F. So this bottom extension here is not necessarily Galois, but there is certainly one thing we can say about it, which is that it is always a separable extension. Okay, but not necessarily normal. So separability is easy to see, because what does separability mean? It just says if you take any element of E, then it has to have its minimal polynomial must be a separable polynomial over F, right? So if you take an element alpha in E and look at its minimal polynomial m alpha of x, minimal polynomial of alpha over the base field, then this must be separable. Okay. But observe that the minimal polynomial of alpha, you can think of alpha as either an element of E or an element of K. The minimal polynomial over F is the same, it's still m alpha of x, right? So observe that if I view alpha as an element of K, okay, then what do we know? Well, we know that K over the base field is separable, and the minimal polynomial m alpha is the same whether you think of alpha as belonging to K or E, right? M alpha of x is therefore a separable polynomial, and that does the job. Okay, so this is more or less a trivial consequence of the definition. So separability sort of is inherited by intermediate extensions, but normality is not so. Okay, and let's give an example where normality will not be there for an intermediate field. And so here's if I take cube root of 2, cube root of 2 omega, cube root of 2 omega square, omega being the cube root of unity, then observe that this is nothing but the splitting field. So over Q, my base field is Q. Okay, so we looked at this example before. K is nothing but the splitting field of the polynomial x cubed minus 2, and it's therefore normal, and it's a separable extension because we are over characteristic 0 where algebraic extensions are automatically separable. Okay, so this is therefore it is Galois because it's both normal and separable. So K over Q is definitely a Galois extension, but here is an intermediate field which fails to be Galois. So we can just adjoin one of them. Let's adjoin only cube root of 2. Then if this is E, observe that E over Q is not a normal extension. Okay, why is that? Because recall, what does normal mean? If I take any element of E, its minimal polynomial over Q must split in E, right? But in this case, if I take the element alpha equals cube root of 2 in E, its minimal polynomial over Q. So what's the minimal polynomial over Q is, well, it's just x cubed minus 2, right? We have shown that x cubed minus 2 is an irreducible polynomial in Qx. Okay, and this polynomial, it doesn't split over E, right? As we see, its roots, all its roots don't lie in E. You have to go all the way to K to get it. So this polynomial is this, and this does not split. In Ex, right? It doesn't split, meaning it doesn't cannot be written as a product of linear factors. Okay, therefore E is not normal. So here is an example of an intermediate field of a Galois extension which is not normal over the base field. So this is not a Galois extension. Okay, of course here we can always say that the top will always be, this will be Galois for sure. So that sort of comes for free. Okay, now what we need to do is, for the second part of the fundamental theorem of Galois theory, we really want to understand when an intermediate field would be normal over the base field. Okay, when do we have normality? So let me state a lemma which allows us to understand this precise situation. So let K over F be a finite Galois extension. Okay, let E be an intermediate field. So just denote it like this. Let E be an intermediate field. Then E over F is normal. So remember, separable is always true. So normality would then imply that it is a Galois extension. E over F is normal if and only if the following is true: that sigma applied to E gives you back E for all elements sigma in the group G of automorphisms of K over F. Okay, so this is the statement that E is stabilized by all automorphisms or by the entire Galois group of K over F. Okay. So let's prove this. It's a easy lemma. In fact, you have seen something like this already when we talked about normal extensions. So recall that this sort of statement should be familiar from our earlier discussion of normal extensions. So we will introduce the algebraic closure. So let L be an algebraic closure of K. This be an algebraic closure of K. Okay, so I have K, now I also have L. There's E, there's F, and of course, as we remarked earlier, an algebraic closure of K, since K is algebraic over E and F, L will also be algebraic over over K, E and F. And so an algebraic closure of K, it's just an algebraic extension of K which is algebraically closed. So this is also the algebraic closure. So you can also think of L as also an algebraic closure of E as well as of F. Okay, so we'll take such an algebraic closure. And what is it that we know about normal extensions? So observe, recall rather, we have talked about this before, E over F is normal, it's a normal extension, is a normal extension. There is a characterization of normality in terms of what automorphisms do to it, if and only if every automorphism sigma, so if and only if sigma of E is E for all automorphisms of L of an algebraic closure which are identity on the base field. Okay. In other words, if I take L, F, take a map from L to L, any automorphism sigma which restricts to the identity map on F. Okay. So look at this, take such a map, then under this map the image of E will just be E itself. Okay. So this will actually go to E, that's what we mean. Okay. And this is equivalent to being normal. Okay. E is normal over F, even only if this happens for every sigma, sigma E is equal to E. Okay. And recall we proved this fact from the definition of normality in terms of splitting fields and so on. Okay. So this is the characterization we are going to use. So what we want to prove is almost this. See, we want to prove this we want to prove it for K instead of L, right? L is the algebraic closure. We want to prove it for a normal extension. We want to prove it for K which contains E, but K is normal. That's somehow the key point. K is normal over F. Okay, so let's actually do the proof now. We have to somehow replace L by K everywhere. That's the broad model. Okay, so let's prove the lemma. So proof of lemma, let's prove this implication first, which is if sigma E is E for all sigma in odd KF, I want to prove that EF is normal. Okay, so what does that mean? I have to show that sigma E is E for all sigma in odd LF. Okay, so maybe it's nice to what we need to prove, is really the following. We want to show that this, so this is exactly normality. Okay, but we want to show that this is the same as sigma E is equal to E for all sigma in odd KF. This is exactly what we are trying to show. Okay, so let's prove one implication. So if it is true over K, okay, so I'll now prove the forward implication. If it's true for K, I'll show it's true for L. If it's true for L, I'll show it's true for K. Okay, so forward implication. So suppose it's true for K. Okay, and we need to prove it for L. So what does that mean? Let's take an element tau, which is an automorphism of L over F, and we need to look at what tau does to E. Okay, now observe K over F is normal. See, this is a normal extension. Means I can sort of use the same argument for K, right? What does that mean? In particular, it means that an automorphism of L, which is identity on F, will send K to itself. This will stabilize K. Okay. Well, what does that say? It means that in this diagram that I was trying to draw here, yeah, when I apply, let's copy this diagram. So I take this diagram. Okay, and so I started with a tau. Okay, I need to understand what tau does to E, but I certainly know one thing, what tau does to K. Okay, what does tau do to K? Well, it maps K to itself. So let's call this tau restricted to K. Okay, so let's consider, let's call it sigma. Maybe sigma is the map tau restricted to K. Okay, this is now an automorphism of K. Okay, and of course its identity continues to be identity on F because tau was identity on F. Okay, so here is an automorphism of K which fixes F. Now by hypothesis, what did we hypothesize? Any such sigma maps E to E. Right, this is what's given. Okay, but then that just means that tau restricted to K maps E to E, but well, tau restricted to K is just tau, right? So tau maps E to E. Why? Because E is further subset of K. Okay, so what does that imply? Well, we have shown that tau maps E to E. This is exactly what we needed to show. Okay, so we assumed that it's true for K and we've shown that it's true for L. Okay, conversely, suppose it's true for L and we want to show it for K. Okay, so let's paste that picture again. So here's the converse. I'll try to prove the opposite implication now. So I know it for L and I need to prove it for K. Okay, so let's start with, so what are we given? We are given a map from K to K. Okay, and so given sigma, an automorphism of K over F, I want to prove that sigma maps E to itself. Okay, I know that this is true if sigma were a map from L to L. Okay, so what I have to do is to lift sigma to a map from L to L. Okay, and recall again that we have discussed this before when we proved uniqueness of algebraic closures and so on. So recall, we can lift sigma to a map sigma tilde. So what is sigma tilde? It's now an automorphism of L. Sigma tilde is a map from L to L. So what does lift mean here? So I mean, i.e., there exists sigma tilde, an automorphism of L, well, it's an automorphism of L such that it's an extension of, well, when I restrict sigma to sigma tilde to K, I just get back sigma. Okay, and recall this is because of the fact that L is algebraically closed. Okay, any isomorphism of the base fields lifts to a isomorphism of the algebraic closures. Okay, this is not a unique isomorphism in general. There are many possible lifts. Let's pick one of them. Okay, but now we are in business because what do we know? We know that what we want to prove is true for sigma tilde. Okay, so now by what we assumed by hypothesis, we know that sigma tilde maps E to E. Okay, why is that? Well, because sigma tilde is an automorphism of L, and I should have said it's a lift, right? Sigma tilde restricted to K is sigma, which means that sigma tilde, when you restrict it to F, will just be identity, because sigma is identity on F, right? So is sigma tilde. So for such sigma tilde, we know E is mapped to E, and so this implies in particular that sigma tilde restricted to K will map E to E, because E is of course a sub of K. Okay, it's the same sort of thing we said for the other part, since E is after all further inside K, and that's all we need to prove, right? Sigma tilde restricted to K is exactly the original sigma that's given. So sigma of E is equal to E. Okay, so proved. That proves the lemma here. Okay, so let's go up and see what the lemma stated. So essentially it said for EF to be normal, all you need to do is ensure that the all elements of the Galois group of K, the automorphisms of K over F. So this is what we usually call the Galois group. All elements of the Galois group stabilize E. They send E to itself. Okay, so recall, I'm not saying that it maps. It's not necessarily the identity map on E. It need not fix every element of E pointwise. It just sends E as a set to itself. Okay, and now we are ready to sort of state and prove maybe a follow-up theorem to the fundamental theorem of Galois theory. So this says that let K over F be a finite Galois extension then, and let's say E, so let's draw the usual figure. Suppose E is an intermediate field, and let G be the Galois group, G be the set of all automorphisms of K over F, and H identity. So let E and H correspond to each other under the Galois correspondence. Okay, what that means is, of course, KH is E, automorphisms of K or E is H. Okay, they correspond to each other under the bijection. Then E is normal over F. Okay, so the normality of EF is equivalent, then E over F is normal, or maybe I should say is Galois, which is the same as saying it's normal, is a Galois extension if and only if H is a normal subgroup of G. Okay, so let's prove this. So we more or less set up everything we need to prove this. So proof. So let's look at, well, let's do the following. Let's look at a slightly more general situation. So suppose sigma is an element of the Galois group. Okay, so G is the automorphisms of K over F. Let me draw the following picture for you. So I have K and F, and E is my intermediate field. Let's do the following. Let's call E prime to be the image of E under sigma. Okay, so E prime is another intermediate field. So here's probably how the picture looks. Both E and E prime are intermediate fields between K and F. Okay, now the question is the following. I know what E corresponds to, right? H is the subgroup that corresponds to E. The question is, what is the subgroup H prime corresponding to E prime? So question, let H prime correspond to E prime under the Galois correspondence, i.e. H prime is just the automorphisms of G which are, of K which are identity on E prime. Okay, then the question is, how is H prime related to then H prime versus H? What is the relationship? Then relation. Okay, so it's a natural question. So E prime, remember, is just sigma of E in this case. Okay, and the answer is rather beautiful. So let's answer this question. To do this, we'll just draw a similar looking figure on the other side. So let G be the group. Maybe I'll draw it right next to this. So let G be the full Galois group. E is the identity. H is the subgroup corresponding to E, and the subgroup H prime turns out to be just the conjugate subgroup sigma H sigma inverse. Okay, so remember, E prime is the conjugate sigma of E in this case, right? So just like E prime, I mean, we usually call this the conjugate field. So just like E prime is obtained from E by applying sigma, H prime is obtained from H by conjugating by sigma. Okay, so let's prove this. It's a rather easy proof. So claim H prime is just the conjugate sigma H sigma inverse. Okay, proof more or less straightforward. So what are H and H prime? H is all automorphisms of K which are identity on E. H prime is all automorphisms of K which are identity on E prime. How do you relate these two sets of automorphisms? Well, suppose I have an automorphism of the first kind, a map from K to K. Suppose tau is like this. It's an automorphism of K which is identity when you restrict it to E. Okay, so when I restrict tau to E, I get an identity. Okay, so from such a tau, how do you manufacture a tau prime which belongs to the other set, which is identity on E prime rather than on E? Well, here's what you do. Remember, E and E prime are isomorphic. Well, they have the map sigma connecting them, right? Sigma is, E prime is exactly sigma of E. So from E to E prime, I have a map sigma. From E prime to E, I have the inverse map sigma inverse. And So let's do the following. Let's just apply sigma and sigma inverse to both sides. So now when you restrict this map, so consider the following diagram. I look at sigma inverse, the map from K to K. Its restriction to E prime is exactly going to map E prime to E, right? That's the definition more or less. And then I look at the next map tau. Its restriction to E is the identity. And then the map after that is sigma, whose restriction to E is now the map sigma, which takes it to E prime. Okay. So now observe that sigma tau sigma inverse is this automorphism from K to K. How does it restrict sigma tau sigma inverse when you restrict it to E prime? Well, it's just the composition of these three maps, which is just the identity map again. Right? It's just going to take any element of E prime back to itself. Okay. So what does that mean? So what we have shown is that if I take H and I conjugate it by sigma, the answer is definitely in H prime. Okay, and now what we have to do is just to reverse the roles of H and H prime. So reverse the roles of H and H prime, meaning repeat the same argument and change sigma to sigma inverse. Okay, reverse the roles of sigma and sigma inverse as well, and do the same thing. You will just get sigma inverse H prime sigma is contained in H. Okay, and that just means you can conjugate by sigma on both sides, containment stays the same. Okay, and which means if you look at these two final equations, this implies that the two are equal. Okay, this means H prime is sigma and sigma is. Okay, now what does that give us? We have managed to prove our claim that H prime is just sigma and sigma inverse. Now what does this mean? So remember, this Galois correspondence is a bijection, right, between subfields and subgroups on the other hand. So we conclude, so by the fundamental theorem of Galois theory, since the Galois correspondence is a bijection, one concludes the following, that E and sigma E prime, so E equals E prime, in other words E equals sigma E, can only happen if and only if H equals the subgroup corresponding to E prime. Okay, and this is true for all sigma. So E equals sigma E if and only if H equals sigma and sigma prime. Okay, this is true for every sigma in the group G. So what does this mean? In particular, it says if H is normal, okay, which means H equals sigma H sigma inverse for every sigma in G, then it implies that E is sigma E for every sigma in G, right? So therefore we conclude the following: H, maybe we should do this in the next page, so let me write our final conclusion here. So saying that H is normal in G means it has all conjugates of H coincide with itself for all sigma in the group G. But from what we said, the corresponding subfields then conjugate, the subfields corresponding to the conjugate is this for all sigma in the group G. Okay, and observe that this was exactly our lemma. So it said that this means that this is if and only if in fact E over F is a normal extension. And this is the little lemma that we proved by our lemma. And finally, the observation we made that separability anyway comes for free. Okay, so normality is enough to say that E over F is a Galois extension. Okay, so that completes the proof of this second part. In fact, we can say a little bit more further. If E over F is normal, well, which is the same as Galois, is Galois, then we know something about the Galois group. Then the Galois group, the automorphism group of E over F, is in fact isomorphic to the quotient group G over H. Okay, so H, remember, is normal, so G over H is actually a group. Okay, so this is the last little bit of this theorem. So maybe I'll make this into a separate lemma as well. And how do we prove this? Well, we more or less proved it along the way. So if you see, what do we know? So I'm going to use the same notation as the proof. So I have K, E, F, I have G, H identity, and I'm assuming that E and H correspond to each other under the Galois correspondence. So, and further the assumption here is that E over F is a normal extension. In other words, it's a Galois extension. So we are assume this to be a Galois extension as well. Okay, so now observe the following. What does it mean to say E over F is Galois or normal? If and only if all elements, so this is the lemma we proved earlier, for all sigma in the group G, okay, which is all automorphisms of K over F. Now what that tells us is the following. I can take the group automorphisms of K over F, and to each element sigma there I can associate its restriction. So there is a restriction map, so let's call it res for restriction. I can restrict any such sigma to the subfield E, okay, and what that gives me is of course an automorphism of E, right? That's what this lemma tells me. So this implies that, E over F is normal, so I just want one implication, implies this is true. So there exists a restriction map which looks like this. It gives me a map from aught KF to aught EF. Okay, now observe that this restriction map has kernel. So this is a group homomorphism. So what are the properties of res? Res is a group homomorphism. That's easy to check because it's doing nothing, it's only restricting it to a smaller subset. Property 2 is that its kernel. So what's the kernel of this map? Well, that's all those elements of sigma whose all sigma in aught KF whose restriction to E is the identity, and well, that by definition is aught KE, right? That's your H. Okay, good. So we are already getting close. So the kernel of this map is H, and so it's a map from G, and the claim is that res is an onto map. Okay, if we do that, then we are done. So the last claim is that res is surjective. Okay, and if we prove this, then we are done. So assuming the claim, this would imply then that the automorphisms of E over F is isomorphic to aught K over F modulo the kernel of the restriction map, which is just G over H. Okay, and that would do the job. So why is this surjective? So what does surjectivity mean? It says if I give you an automorphism of E, so let's say I give you a map tau from E to E, which is identity on F, then you should be able to find a map from K to K such that tau is the restriction of that map, right? So that's what ontoness of res will mean. So given tau from in EF, want to find an element, shall we call it tau tilde maybe, in aught KF such that the restriction of tau tilde to E is tau. Okay. Now, well, I don't offhand know how to do this extension to K, but there is something that I know how to do. Okay, and that's our theorem on algebraic closures, which says given a map given a map from E to E, I can always lift it to its algebraic closure. Okay, so let's take the algebraic closure L. So again, I'm using the same notation that we used earlier in the lemma. So L now is the algebraic closure of K, if you wish. Okay, so I can certainly lift tau there. So let's call that map as tau bar maybe. Okay, the lift of tau. I mean, there are many possible lifts, but there definitely exists one lift. So recall the following fact about algebraic closures, that there exists a map tau bar, which is an automorphism of the algebraic closure L, and of course it fixes the base field there exists this such that tau bar restricted to E is tau. Okay, because its restriction to E is tau, that's the reason why it fixes the base field. Okay, because tau fixes the base field. Okay, but how do we get tau tilde? We don't want to go all the way to the algebraic closure. I want to get a map from K to K. Okay, now observe, this will come from the normality of K. So now I can think of K as being in the middle, and now observe K is a normal extension of F, right? And what does normality give you? It gives you precisely this, that any automorphism of the algebraic closure will map this K to itself. Okay, so again, so we sort of are using all the various facts we have seen before. Recall K over F is a normal extension. Will tell you the following, that tau bar must map K to itself. And now we are in business. That's exactly what we need. So let's take this tau tilde now to be just the restriction of tau bar to K. So that will finish the job. So now define tau tilde to be, take tau bar and just restrict it to K. So we know it maps K to K, so you can restrict it to K. Okay. So what is this? This is now an automorphism of K for sure. When you restrict tau tilde further to E, well, it's the same as tau bar restricted to E, right? Tau tilde is really the same as tau bar when you restrict to K. So definitely when you restrict further to E, but this is just tau by definition. So again, because it's tau, it fixes the base field pointwise. Okay, so that's exactly what we wanted to prove. Okay, so that's the end of proof. So this completes all the various parts of the fundamental theorem of Galois theory. So we'll look at some applications next.